Everybody, welcome to Video Notes 2.1. We're going to be doing 1, 2, 3, 4, 5, 6 things. So, playing the jump up song. I want you to make sure you read chapter 11, these sections. At the end of the video notes, there'll be a couple of questions I want you to answer. Okay? Oh, hey, see if you get it. Alright, so we've been spending some time talking about atoms, and now we're going to talk about where the electrons really are. Okay? So, Bohr was right that electrons are in energy levels. Bohr was not right that they're in rings. Okay, so energy levels can be represented by these whole numbers. Okay, first energy level, second energy, third energy level, fourth energy level. Okay, each energy level has sublevels in it. Okay, S, P, D, and F are kinds of sublevels. First energy level can only have one sublevel, so it's going to be an S sublevel. How many orbitals does that have? It just has one. So how many electrons could fit in that first energy level? 2. You may remember these numbers, 2, 8, 18, from your discussion of rings in the past. So how many electrons can fit in the first energy level? 2. Second energy level, 8. Third energy level, 18. Fourth energy level, 32. But now we're going to see where they are in those energy levels. So if you're thinking of rings, remember rings are wrong, but here's the nucleus, all right? In that first energy level, there's only one sublevel, so only 2 electrons can fit. Right? Then you go to the second energy level, and it's a little further from the nucleus, so it could have 2 sublevels, an S and a P sublevel. Okay? The P sublevel actually has 3 different kinds of orbitals, or 3 orbitals that are equal energy. You get to the third energy level, you can have 3 sublevels, the S sublevel, the P sublevel, and the D sublevel. All right? So let's explain. I'll explain a little more in the next slide. So here is the nucleus again. All right. You see that first sphere? A sphere represents an S sublevel. S's are spherically shaped. That means the electron is probably inside that sphere somewhere. There's a high probability chance. If we mapped out the probability, this would be like the cloud around, or the barrier around the probability of finding an electron there. S's are spheres. Okay. So first energy level has an S. Second energy level has an S orbital as well, or an S sublevel. And it's also a sphere, but look, it's a little bit bigger. All right, S is spherically shaped. The second energy level has a second sublevel called the P sublevel. P sublevels kind of look like a figure 8. If you mapped out the electron density, it'd be like chance of finding an electron somewhere in that area. But there are 3 different P sublevels. They all have the same energy. So P looks like this dumbbell shape or this figure 8 type shape, and there's 3 lobes along the X, Y, and Z axis. Then third energy level also has a sphere. Okay, but look how much bigger it is. Third energy level is P orbitals, but they would be bigger, 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 bigger. All right. Third energy level also has D sublevel, and there are 5 different ones. So I'd have to draw all 5 of these pictures right here on top of all those pictures. All right. And then finally, the fourth energy level has what is called an F sublevel. So how can we describe electrons? We can use 2 ways. Orbital diagrams and electron configurations. But there's rules. The first rule, not the first rule, but one of the rule is start at the lowest energy level, fill up that sublevel, and then move on. Okay? This is off-Baugh principle. Okay, so here's the name of the rule. Okay? And here's what it means. Fill lowest energy levels first. Second rule is only 2 electrons can fit in an orbital, and they have to have opposite spins. That's the Pauli exclusion principle. All right, principle. So how many electrons can fit in an orbital? 2. And they can't be the electrons with the same spin, electronic spin. Okay. Third energy level, third rule, or the third rule on this list, put 1 electron in a sublevel until it's half filled before you double up. And this is the Hund's rule. Hund, H-U-N-D-S, Hund's rule. Okay. So these are 3 rules that are going to guide us when we're drawing orbital diagrams or writing electron configurations. So let's start. Orbital diagrams. You can use circles or boxes to represent an orbital. Okay. The lowest energy level is the 1s, so it's down here closest to the nucleus. You can write them going up the page or going across the page, but you always do lowest energy level to highest. Okay. The lowest energy is 1s. Each electron is an arrow. So what element is represented here? Well, let's count electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 electrons. So this is potassium. How do I... Oh my goodness, Harbin. potassium, how do I know? There's 19 electrons, and potassium has 19 protons, so this is the neutral potassium atom. So this is potassium because it has 19 electrons. All right. Now, how about here? Well, 2, 4, 6, 8, 10, 12, 14, 15, 16 electrons. What element has 16 electrons? Well, when it's an atom, sulfur has 16 protons, so it has to have 16 electrons. Okay, so let's look at the 3 rules. Aufbau principle, building up, filled, 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 moved up, and then I got to there, and I had to stop because I ran out of electrons. Okay, filled, 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 sort of. Okay, look, I had to put 1 electron in each before I doubled up because that's Hund's rule. So in the 3p orbital for sulfur, there are 2 unpaired electrons. Okay, so orbital diagrams are boxes or circles that represent the orbital, and you use arrows to represent electrons. What's an electron configuration? Well, it's taking that orbital diagram and making it more condensed. And so an electron configuration, this was the orbital diagram for sulfur, still 16 protons. This one has 16 electrons. So we say 1s, and how many electrons? 2. That's not 1s squared, that's 1s2, 2 electrons in the 1s orbital. 2s2, 2 electrons in the s orbital of the second energy level. 2p6, this is all on the same line, 3s2, and then 3p4. Why do I stop at 3p4? Because the 3p sublevel only has 2, 3, 4 electrons in its set of 3 orbitals. Okay, so an electron configuration looks like this. An orbital diagram looks like this, or it's going up the page, but sometimes we write it across because it fits a little better. Okay, so you should draw this in your notebook, because how are we going to ever remember which orbitals to put the electrons in? Well, write this out first, okay? Once you have that written out, then you do a diagonal arrow. Fill the 1s first, then the 2s, then the 2p, then the 3s, then 3p4s, then 3d4p5s, 4d5p6s, 4f5d6p7s, 5f6d7p. Now, using that many arrows would get us through every element on the periodic table, because they would be filling up and we'd get through a lot of elements from a lot of electrons. Okay, a lot of elements with their electrons. So you should be able to draw that. So let me go back to, I could erase this. You would start by drawing that and then fill in your arrows so that it looks like this. Okay, so let's practice. We want the electron configuration for a sodium atom. So I write Na for sodium, 11. And then I fill the 1s. Only 2 electrons can fit in an s orbital because it only has 1 shape and it's a sphere. Then I could put 2 electrons in the 2s. Again, only 2 can fit in the s orbital because it's a sphere. Then I go to 2p. In the 2p, there's 3 orbitals of the same energy, so I could put a total of 6 in that sublevel. And then that's filled up, so now I'm going to 3s, and I only have 11 electrons, so I would put a 1 electron in the 3s orbital. So this is sodium's electron configuration. What about for the sodium ion? Well, at this point in time, I'm telling you that sodium is a loser and has a +1 charge. Okay? I'm telling you that. Eventually in this chapter you'll know why. So then, so this means that there are only 10 electrons. So 2 of them go in the 1s, 2 of them go in the 2s, 6 of them go in the 2b, and then we stop. Because this is 10 electrons and 11 protons for an overall +1 charge. So this is the ion. How do I know? Because sodium's got 11 protons and 1 less electron. This is the atom because 11 protons, 11 electrons. Okay. Now, you can memorize this filling diagram if you want, but we are always going to have periodic tables. If you label this, you can see that there's 7 rows on the periodic table. Those 7 rows correspond to these 7 energy levels. Okay. The first row is the first energy level, and it's small, so guess what? There are only 2 electrons, 2 atoms, and so that's the first energy level. It's filled when you get to helium. Okay. Then if you come over here, then this is going to be lithium. Lithium has 3 electrons, so then you'd have to put 1 of them in the 2s1 orbital. Okay. If you get to beryllium, there's 4 electrons, so then it would end in 2s2. So what I mean by that is beryllium's electron configuration, because it has 4 protons, so it's going to have 4 electrons. It would be 1s2, 2s2. Look at the energy level corresponds to the row, okay, and the s corresponds to the left side of the periodic table. If you look over here, there's 6 boxes. And so it also corresponds to the total of 6 electrons that can fit in the 2p sublevel. And that would be this part here, 2p, and you can fill up to 6. Then we go back to the third row, 3s. 3s can hold 1, 1, 2. And then we jump over to 3p, and it could hold up to 6. Right? Here's where it gets a little weird. 4th energy level, the s orbital, the spherical orbital in 4th energy level can hold 2. But that fills before the 3D orbitals. Now the D ones were those funny ones that kind of looked like flowers, and there were 5 different ones. So 1, 2, 3, 4, 5 orbitals for a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So then it'll go 3D 10, and then we're back to the 4th row. 1, 2, 3, 4, 5, 6, 7. Not back to the 4th row, still in the 4th row. So for the p orbitals, the number in front of the orbital matches the row that you're in. Okay, we'll practice using that. Okay, so here's where it gets a little tricky. The d orbitals have 1 less energy level number than the s orbitals. Okay, so is there a shorter way to do this? There's something called the noble gas electron configuration, and here's what you do. You start with the noble gas. You're probably saying, noble gas, what's that? This last row on the periodic table are called the noble gases. We'll learn more about that, but for now you just need to know that they're the noble gases. Noble gases are stable, they don't react. So their electron configuration is stable. And so we can use that as a starting place for an element that has more electrons than that. So let's find barium. Barium's right here. Okay. And let's find how many electrons. So this is going to be 56. Okay. And then we find the noble gas that comes before it. So 55, 54. The element xenon is the element in the very last row on the periodic table that comes before barium. Okay, you can only use this row. You put it in brackets, and then you go to the next row. 1, 2, 3, 4, 5, 6, 7. And so we're in the 5th row. We're on this side of the table, so we're S, S2, and xenon takes care of 54 electrons. So this is plus 2 more is 56. So this is called the noble gas, or shorthand, electron configuration. Okay, valence electrons. Once we start looking at the electron configurations of all the elements, we're going to find out that the valence electrons are the outermost electrons. They are the outermost electrons in highest energy level, present energy level, S and P electrons total. Okay, so make sure to write that down. Valence electrons are outermost electrons, but they're the outermost electrons in the highest energy level, S and P sublevels total. Okay, so hydrogen is 1s1. Guess what? It has 1 outer electron in its highest energy level, so it has 1 valence electron. 1 valence electron. Let's look at lithium. Lithium would end in 2s1. So highest energy level for lithium would be the 2nd energy level, 1 electron, 1 valence electrons. These elements here have 2 valence electrons. If we jump over here, 3 valence electrons, 4, 5, 6, 7, 8 valence electrons, except for helium. Helium only has 2 valence electrons. Okay, valence electrons. So this would be 2p. Over here is 2s, 2. So 2, and then we get to here, 2p6, 8. So, plus 6 is 8. So all of the elements starting with neon and going down with those noble gases have 8 outer electrons because their 2s energy, 2s sublevel is full, and their 2p sublevel is full for a total of 8. Okay, so we'll keep working on that. Valence electrons help us determine charge. Remember, 8 is great, and we'll get to that soon. So let's play what element am I? So we're looking, and we can count here, 2, 4, 10, 12, 18, 19. 19 electrons. So let's look, and it just happens to be potassium with 19 electrons. Okay, what element am I? There's 10, 20. So we're looking at calcium because that's 20. Now, remember, elements are atoms. Atoms are neutral. So these don't have charges on them. But what if it's an ion? For instance, where do we start with this? Okay, well, I'll tell you that this is 4 and 9 is fluorine because it has 9 total electrons. Okay, but what if we add 1 more electron? Well, then it's going to have 10 electrons. So I'm telling you it was fluorine to start with. It got an extra electron. So it's going to be fluorine's nucleus, but that one extra electron gives it 10. So now it has 10 total electrons. So this is the fluoride ion electron configuration. This is a fluorine atom. Atom, ion. Okay. All right, ground state versus excited state. So we're saying there's an electron here. Remember, rings are wrong, but I'm using this as a model. Okay. If you add energy, okay, that electron could jump. Okay. That's why I was playing the song Jump Up. All right, so ground state is here, add energy jumps up, okay? But then when that electron jumps back down, it gives off that energy in the form of light, okay? So if there wasn't this arrow, so before this electron's in the second energy level, so this is ground state. All right, ground state. It jumps when that same electron that used to be here jumps up. That's called excited state. All right. When that electron goes back down, it's back to ground. Back to ground. Okay. So what happens when you add energy to elements? They absorb that. The electrons absorb energy and jump up to the excited state. But when that electron jumps back down, it gives off a certain wavelength of light, and that's colors you see. That's why flame tests work. That's why atomic spectra work. Okay, and that light energy you see is the effect of the electron jumping back down to the ground state. Okay, let's see how we can represent that in orbital diagrams. Here's beryllium. How do I know? 1s2, 2s2. That's got 4 electrons. It's a beryllium atom. Okay, this could be a beryllium atom in an excited state. What happened? One of the electrons got promoted with energy to a higher energy level. Okay, how do I know this is still beryllium? Whoopsie. This 1s2, 2s1, 2p1, it should fill here before we go to here, but this is at a higher energy level because it must have absorbed energy. Okay, so an atom in an excited state, if I know it's beryllium, it has 4 electrons, they should all be in the right filling order. Okay, but if I'm telling you this is beryllium and that one's up there, it must be beryllium in the excited state because one of its electrons is not following the filling order. Okay, please read chapter 11. Those sections. And now I really want you to answer these 3 things, okay? What does the SP and D and F tell you about the orbital? Page 315 should help. Read through example 11.2 on page 318. And then make sure you could describe the difference between a 1s and a 2s orbital, okay? Also, page, this must be self-check 11.2. It's on page 321. It says in red that's self-check. It says to do a whole bunch of elements, but I want you to make sure you can do silicon. Okay, thanks for playing. As we review, electron configurations are periodic, so the table's going to help us. Periodic table's going to help us. All right. Oh, I wrote gonna. All right. Now, use your rules. Off-ball rule, Pauli exclusion principle, Hund's rule. Use your rules. Valence electrons are outermost S and P, and valence electrons, this is previewing for what kind of fun's coming, they're used for bonding. Okay, so make your electrons jump up to tell the difference between ground state and excited state. What causes that? Define valence electrons, compare the orbitals, size, shape, order of filling, and electrons that can, how many they can hold. Use your rules, and then do electron configurations and orbital diagrams. Peace out, guys.